Here's a math problem that I'm working on involving bracelet permutations with and without directed beads. Directed beads have features that allow you to tell whether the bead is pointing clockwise or counterclockwise. The problems are based on these two bracelets that we got during October with a Halloween theme. First is the skull bracelet. It's got 16 beads, half red and half black. The beads are directed because they're in the shape of a skull, and we can use the jaw to indicate clockwise versus counterclockwise. Second is the pumpkin bracelet. It has 38 beads, half silver and half orange. The silver beads are smaller than the pumpkin-shaped orange beads, but that doesn't matter for the bracelet problem. What is interesting here is that the silver beads are traditional spherical beads in which you can't tell if they are pointing clockwise or counterclockwise, but the pumpkins have faces, so they are directed beads. For each of these bracelets, we want to figure out exactly how many different bracelets we could make if we took apart the bracelets and reassembled them in all possible arrangements. In a bracelet problem, we can't tell apart any bracelets that can be rotated or flipped into an identical arrangement. For the classic bracelet problem, we treat all of the beads as if they were perfectly spherical, so that only their color matters. For the directed bracelet problem, the beads are asymmetric, so that we're able to tell if they're pointing clockwise or counterclockwise. We also have a hybrid situation, like the pumpkin bracelet, where the beads of one color are directed and the beads of the other color are not. So in the weeks ahead, I'll be working on these problems and will hopefully post a solution with explanations. I'll solve the classic bracelet problem corresponding to the skull bracelet with 8 red and 8 black beads, temporarily replacing the skulls with spherical beads of the same color. I'll give an exact number and I'll break this number down into relative frequencies and how many distinct bracelets have the same relative frequency if the bracelet were randomly assembled. In the case of random assembly, not all bracelets are equally likely to happen. In fact, the more symmetry a bracelet has, the less likely it is to occur. So I'll tell how many bracelets have each possible value of relative frequency, or odds of occurring, and all of the relative frequencies will add up to 1, as they must in probability problems. I'll do the classic bracelet problem for the pumpkin bracelet as well, with 19 silver and 19 orange beads. Again, for the classic problem, we replace the pumpkins with spherical orange beads so we can't tell which direction they're pointing. Again, I'll give an exact number and a breakdown into relative frequencies, and when we add up all the relative frequencies, we'll get exactly 1. Next, I'll solve the directed bracelet problems that arise from the actual bracelets we have. I'll do the skull bracelet with its 8 directed red and 8 directed black beads, as always give an exact answer and relative frequencies. And finally, I'll solve the pumpkin bracelet, a hybrid case with its 19 directed orange beads and 19 spherical non-directed silver beads. Some background. Back in high school, I was preparing to take the Math Level 2 Achievement Test, and there were certain types of permutations you were expected to know. First were ordinary permutations, where n distinguishable items are arranged into n distinguishable positions, and there are n factorial ways to do this. The logic is that you have n choices for the first item, then 1 less, or n minus 1 for the second, then 1 less than that, or n minus 2 for the third, and so on until you run out of items. Next were permutations with repeats, where you divide by a factorial for each repeat. So if you had 9 items and 9 positions for them, but the 9 items were 3 red, 4 blue, and 2 yellow, the answer would be 9 factorial divided by 3 factorial divided by 4 factorial divided by 2 factorial, or 1260. After that were circular permutations, where n different items were placed around a circle and you couldn't tell the various rotations apart. The classic way to present this question would be to ask how many ways can n people sit around a circular table. The answer would be n minus 1 factorial, and the logic would be to pick a reference person and rotate him into a reference position, so that there are then n minus 1 remaining people who you can assign freely, and that's an ordinary permutation, so there are n minus 1 factorial different ways. Finally, you are expected to know bracelet permutations when all of the beads were different. They often use key rings and keys instead of bracelets and beads to present these types of problems. The answer is n minus 1 factorial over 2, and the logic is that you get the n minus 1 factorial from the circular permutation, and the fact that you can flip it over cuts the number of permutations in half. You are not expected to be able to do circular or bracelet permutations with repeats. The problems become complicated. They often require individual analysis of any possible symmetries or patterns that can be caused by the repeated beads. For example, In a circular permutation of n distinct items, equally spaced along the circumference, if I temporarily disallow the circle from rotating, this reverts to the basic permutations where there are n factorial possibilities. But once I allow the circle to rotate through its n rotational positions, I get n distinct patterns which are equivalent under rotation. This allows me to divide n factorial by n to get n minus 1 factorial, the number of circular permutations. If there are repeats, I may not get n distinct patterns as I go through the n rotations. The pattern may have some type of symmetry, which results in repeated arrangements, and therefore fewer than n distinct patterns occurring as we rotate the arrangements through the n rotational positions. For example, in alternating color patterns, like our bracelets, there are only 2 distinct patterns in the n rotations. For bracelet or keyring problems where you can flip the arrangement over, there are even more possible symmetries. In a circular rotation, the symmetries are related to the factors of n, so the skull bracelet with n equals 16 may be a harder problem than the pumpkin bracelet with n equals 38, despite the fact that 16 is smaller. This is because 16 has more divisors than 38. Because of the dependence on symmetries and divisors, bracelet problems with repeats defy most attempts to reduce their solution to formulas in a handbook. As a result, detailed logical analysis is required, and you will need sharp deductive reasoning skills and plenty of time to think it through. Have fun.